Hello everybody, welcome to our second video here. This is going to be the second video that we're going to do that's asynchronous. It's actually our fifth topic. This is topic 5 on vectors. This is going to be our second asynchronous video. Again, our goal behind these asynchronous videos is that you guys can go at your own pace. You can pause, you can ask questions. If I'm going too slow, you can speed it up. If I'm going too fast, you can slow it down. And so that's our goal. And so I'm not going to spend too much time on that because we've already discussed that. So let's hop right into our second topic, which is on vectors. And so you can see our topic is vectors. And really this isn't new at all because we've talked about vectors before. Here's a definition. Vectors are anything that has a magnitude, like say, let's say 12 newtons. And it has a direction, like say south. All right, if you had something that was just magnitude only, it would be considered scalar, like say 1.2 kilograms. That you really can't attach a direction to. It's a mass, right? You can't throw a direction on it. Now, one of the things that we like to do to help visualize and keep track of multiple vectors, multiple things happening at once, is we like to use arrows. You can see right here we like to use arrows. The main goal being that the arrows have what we call a tail and a tip. And the tip really is the like the arrowhead. That's really like what we like to designate as the vector tip. And so that really gives us the direction, because whichever way that vector is pointing, whether it's side to side, whether it's up and down, whether it's kind of on a bit of an angle, that kind of tells us which way things are going. And again, this is really important because there are some times when we really only have one direction of travel, up or down or north or south. But sometimes we go north for a while, then south for a while, then 45 degrees east of west for a while. And because we have all these different possible directions, it's nice to keep track of them. And that's what vectors do. That's basically the goal here. So on this next slide right here, I got kind of a visual to kind of illustrate how the length of the vector line, really the longer the line it is, tells you how much magnitude it has. And maybe another word we could use would be strength. So the more strength of the vector, the longer the line. See, this line right here is only from here to here, right? And this line right here is from here to here. If I were to pick those up, I wonder whether I can do that here. If I were to pick these up, well, okay, maybe I can do it like this. There we go. And put them there to there, and pick these ones up and put them there to there. In theory, we should be able to add vectors to each other. And well, clearly this is not quite to scale because it went a little bit beyond. But hopefully you get the idea, is that they should be something we should be able to add to each other. As an example, let's say that I went 3 meters, and then I went 7 more meters in the same direction. Well, now I've gone 10 meters. But what if I went 10 meters, and let's just call this, for the sake of argument, let's just call this left. Well, let's call it right, I guess, because we're going right. There we go. And then you go negative 3 meters. And so if you're still going negative 3 meters to the right, it really means you're going to the left, right? A negative right really means you're going left. Well, that means at the end of the day, the net amount you've gone is 7 meters towards the right, because these ones are really subtracting, right? Like this amount right here has to be removed from what you had. Well, same thing with these up vectors, right? And so what we're trying to do is we're trying to have like a visual picture to help keep track, again, of multiple things happening. Now, my next slide gives a couple of vector conventions, things that are considered to be standard ways that we draw things, so that we're all working off the same set of rules. Really, that's what a convention is, right? We could have done these things different ways, but we always like to do it more or less the same way so that everyone kind of understands, okay, here's what we're going for when we draw a vector arrow. So the first one, we always draw the arrow in the direction of the vector. I mean, that kind of makes sense. Why would I say, hey, someone is going north, and I draw it that way, which is south, right? Like we should draw it the right direction. We always like to have square brackets in directions or some sort of compass, right? Like this one right here, you can see it said 35 degrees. That's going to imply that from the axis to there is 35, and that way we know more information. Second one, I already kind of talked about this. The length of the vector is proportional to the magnitude. And so if I show you a little vector that's going this far, or a larger vector, you know that this one, say, could be 1 meter, and this one here could be 9 meters. It's because it's 9 times bigger. Number 3, vectors can be moved around as long as it maintains the same magnitude and directionality. And this is where this is kind of a useful kind of concept. It goes with the next blurb, so I'm going to draw more here. Imagine that I were to have someone that is pushing in this direction here. Imagine I have someone that's pushing in this direction right here. So let's see that this guy right here is pushing with 15 newtons, kind of on an angle. I won't even give you the angle right now, we'll just say that it's on an angle. And this guy right here is also pushing with 15 newtons. Well, what's kind of cool about this is that I know which way the final object is going to move, right? And the reason why, you can probably even picture this. If one goes kind of slightly up and over, and this one goes slightly up and over, hopefully you'd agree that, well, when you push like that, hopefully the object is going to kind of go forward. And one of the ways that vector addition, and that's really what topic 4 discusses, is that when you add them to each other, you always have to have them go tip to tail. And so currently, this red vector going mostly up to the right, and this vector that's going up and to the right, right? I mean, hopefully we agree that it's going up, but we really haven't made this like fit properly. This is where there's going to be a lot of trigonometry. What I'm going to do is I'm going to pick up this vector right here. Oh, I was hoping to pick the whole thing up. Hang on one second. Let me erase this just so I can put another color, because I need to use this to prove a point here. Let's use a different color entirely. Let's use green. Okay, so same vector kind of going off on the angle here. 15 newtons. They're both the same, right? And we kind of agree that if they were both to get pushed, purple would be how it finishes. Oh, I should use some terminology here. This is known as the resultant. The resultant is basically what's going to happen. Red is going to push, green is also going to push, purple is the way in which they're going to travel. Well, what we can do as a way of kind of illustrating this is we can take this vector right here, and we can move it to there. And this is called the tip-to-tail method. And so even though these two vectors are pushing at the exact same time, we can almost consider it to be a little bit different. We can consider that the red vector first pushed, and then afterwards the green vector pushed, and then the purple vector, which of course isn't all in one big piece, but hopefully that makes sense. Well, the purple vector should actually have been that big, and we call that a resultant. And it always makes a triangle in the work we're going to do. Right? Let me try to explain that one more time. So red is going to push this way here. Right? Green is also going to push. But hopefully we kind of recognize that if they both push in opposite directions, they're kind of going to cancel each other out in the x dimension. But in the y direction, this purple line here, which we call the resultant, it's really where things are going to move. Things are actually going to move in an up direction. But we can consider this, even though red and green were pushing at the same time, we can consider them to have like pushed one after another. So if red pushes for a while, and then green pushes for a while, well then the net resultant would be here. And really, this is the exact same thing as if we were to do like, just say distance vectors. Let's say that I said you walked this way for a little while, in blue. And let's say that I said you were to have walked this way for a while in green. If I were to ask you how far you've really traveled, in yellow, I'll do a dotted line. It's how far you've actually traveled, right? This was your start, this was your finish. But we can just say that, well, one at a time, blue first happened, and then green then happened second, and then yellow is how it finished. And so we call this tip to tail, because the tip of this vector right here is meeting up with the tail of this vector here. And really the yellow is the net. Only the word we don't use the word net, we use the word resultant. So hopefully that makes sense a little bit, is that we can consider these things to be happening independently rather than happening at the same time. They can be happening at the same time, but we can kind of consider them to be like one after each other. And it kind of simplifies, especially more complicated problems. Because that's what we're going to get into in the next part of this unit. We're now halfway through kinematics. We're now going to get into some more complex problems, which usually involve more than one thing happening at once. So we're going to do a couple examples, but before I get to that, I need to point out that when we do vectors, they're often going to work in different dimensions, like say the x and the y dimensions, right? Because it's going to be fairly rare that things go exactly east or exactly west or exactly north or exactly south. They're sometimes going to go on angles. And so we need to consider how to work with that. Now, I do need to point out there are actually 3 dimensions. There's x, y, and z. But we're only going to work with 2 dimensions. And it's typically for us going to be x and y. Okay? But in theory, there are kinematics questions that can be done in a 3rd dimension. And here's what's really important about that. When we do something in 3 dimensions, like say you go right along the x-axis for a while and right along the y-axis for a while. Well, what that means is that if you know that this angle was, say, 40 degrees, we can actually calculate the hypotenuse because we know a couple of math rules. And so this is where math and physics really rely on each other. One of the rules you need to know is that c squared equals a squared plus b squared. It's Pythagoras' theorem, which means that if you ever know, say, 1 or 2 of the sides and it's a nice right angle triangle, you can actually solve for the 3rd using Pythagoras' theorem. And then the other rule you need to know is something called SOHCAHTOA. These are known as your primary trig identities. And this is knowing that sine of an angle, we'll say 40 degrees in this case, will be the opposite over the hypotenuse. And I'm just going to write out what it would be for this statement here. If this is my angle of 40 degrees, this side over here is known as the opposite. This x side right here is known as the adjacent. And the hypotenuse would be the longest side. And so if you need right now would be a great time to pause the video and say, Chris, I'm shaky with my trigonometry. I know I took Math 10-C, but I'm not great at trig. I can give you a little tutorial on this. But those are two things you need to know how to do. Your sine is opposite over hypotenuse. Your cosine is adjacent over hypotenuse. And tan is opposite over adjacent, as well as Pythagoras' theorem. Those are all skills that are must-have. We need to have these skills down because we need to be able to consider the x and y dimensions of things that are going on angles. So I want to begin by just using an example. Let's say that I told you that the opposite side over it, not the opposite side, but the longest side across a soccer field was 150 meters. Well, the reason why I know this is 150 meters is that hypothetically, let's say that I solved for this side right here being 120 and this side right here being 90. Right? What should happen then is 90 squared plus 120 squared, that's a squared sign, should equal c squared. So if you square root the whole thing, you should get the hypotenuse. So if you want to, just grab a calculator, try this out. 90 squared plus 120 squared. And then I get 22,500. If you square root the whole answer, you do get 150. Right? And so that's one skill you need to know, which tells us that, like, if I know that the side is 150, we may be actually able to find the component parts of them. And that's going to be a really important skill. We're actually going to go backwards sometimes. I'm going to give you what the hypotenuse side is, and we're going to be asked to find what the components are. And the only way we can do that is if we know an angle inside here. Now, in this particular example, we weren't given an angle, but we could find one. For example, I could tan inverse my opposite over my adjacent, and that should give me my angle. So if you can follow along here, if I tan inverse 90 over 120, this angle right here is about 36.8, etc. degrees here. And you could have done that from tan. We also could have done it from cosine. I could have inverse cosined the adjacent over the hypotenuse. And remember, the hypotenuse is always the longest side, right? So 150 definitely has to be your biggest number. So if I inverse cosine 120 over 150, hey, look, I also get this same number here, 36.8 degrees. And the final identity I could have worked with was sine inverse. I could have done 90, the opposite, over the hypotenuse. And really, all of these would have given me this angle. And so all of these pieces, they kind of work in concert with each other. And so I think that's all I'm going to do for like my preamble on trig. I'm going to do some examples now. And again, this is the reason why we're doing this video asynchronously, is that there's going to be different levels of math comfort. I just realized before I get to this last example, I've got one more thing I've got to show you. Unfortunately, in physics, we really didn't think this through all that well, but there are multiple different ways that you can actually measure angles. And it's a shame that we didn't just go with one consistent one, but there are actually two ways for sure I need you to know. And there's actually more than two ways we measure angles, which is kind of a pain, so you have to be familiar with all of them. Here's the first one. This is called the polar coordinates method, and it's what we do in math. So any of you guys who have done math 20-1 or 2, you already know this idea. It's this picture right down here in the bottom corner. And what ends up happening here is you start on the positive x-axis at 0 degrees, and you start going around the circle clockwise. And that means if you go all the way around the circle once, it's 360 degrees. And so that means that straight up is 90. So north would be 90, basically. True west would be 180. And then basically that's the concept. It's actually based on the idea that the sun rises in the east and sets in the west, and so east got to be 0 degrees. That's one way of measuring an angle. Another way of measuring an angle is based on the navigator method, which is north, south, east, and west. And what ends up happening here is you have to give it like south of west. So if it says south of west, it means that you are mostly traveling west, and then you're going just south of it. And so you have like a little offshoot right there. There's another way of writing this one. I like this one. It means that you're going mostly west, and then you went 60 degrees to the south. And this is what I'll probably write on most of my answer keys, just because it's very succinct. And it's also something that you can do kind of very quickly. Go mostly west, go 60 to the south. And these two things mean the same thing as each other. It's weird because the S and W are backwards, right? This says south of west, and this says go west, and then go 60 degrees south of it. And so they mean the same thing, just in different orientations. There's actually one more way of measuring angles, and this is one that we rarely use, but this one actually involves making true north being 0 degrees, and I believe they go around the circle clockwise, and so that would make this 90, and that would make this 180, and that would make this 270. And that one's really confusing, because, I mean, in math, if we've learned that 0 is basically on the x-axis, well, now it's on the y-axis, and it goes clockwise, not counterclockwise. So there's another method you can have. I forget what it's called. But you need to be familiar, basically, with all of these, and hopefully it will tell you in a question what the angle is. But you need to be able to problem solve that. So, okay, now let's get to our problem. So here's what we want to do. Let's say that I give you a scenario. A car drives 10 kilometers east. So I'm going to use different colors as I do this. Let's have something drop 10 kilometers east. So there's a line, and I'm going to draw the arrow pointing this way because that's east. And I'm going to say this is 10.0 kilometers. And it says, and then it goes 7 kilometers north. So if I use a new color, and then 7 kilometers north. Now I'm not going to draw it quite as big, because this was 10 kilometers, so to scale, this should be about 7 kilometers. Okay. And you'll notice that what we've done right in this location down here, I'm even going to use another color to point this out. This is known as the tip to tail section right here. This is tip to tail. Because what's happened is the tip of the black arrow is lined up with the tail of the red one. Now if we do that, what we can then do is say, well, this is the start and this is the finish up here. And so then I can draw what is the resultant. And the resultant is really this one right here. I'll draw the pink dotted ones. Pink is now my resultant, which is always probably your hypotenuse. Right? And so in doing so, now what we've got here is kind of a triangle scenario going on where it asks, well, how far have you really traveled? Now, I mean, if we don't care about direction, the answer is 17.0 kilometers. That's if we're going to do a scalar displacement. If we were just to do d without an arrow hat, it's 17 kilometers because direction doesn't matter. But if we do care about direction, we need to care about, well, like from start to finish, where do we finish up at? Right? So here's where we have to use those math skills. You're going to have to use c squared equals a squared plus b squared. And you're going to have to solve. So this is going to be the square root of 10 squared plus 7 squared. That will be what your hypotenuse is. So calculator time, 10 squared plus 7 squared, all square rooted, and I got 12.2 or so. And we still have to do sig digs, which means that 7.0 has 2 sig digs. So we're going to say this is 12 kilometers. It means that we actually only went 12 kilometers from start to finish, right? Because, I mean, in a way, you kind of went out of your way to go a place, right? If you could cut right across a field, just like the example back here, if you could cut right across the field, that's the shortest way of going. If you've got to go the long way around, it's not quite so fast. But there's one more thing we need to know, though. If this is truly a vector, we need to know a direction. And so what we're really looking for is this angle right here. And so whenever you're solving for an angle, you're always utilizing sine, cosine, or tan. I'm going to recommend tan inverse is almost always my go-to because it's always your opposite, which in this case is 7.0, over your adjacent, which was 10.0. And again, if you're a little fuzzy as to how the heck I'm doing that, now's the time to call me over. Right? Because this is like a previous skill that hopefully you have back from Math 10C. This isn't even a Math 20-1 or 20-2 skill. This is hopefully from 10C. But if you're a little fuzzy on how in the world I've calculated this angle right here to be 35 degrees, let me know. Now, if we agree, though, that this angle is 35 degrees, we just need to know how we want to write it. And so one of the ways we could write it is just as 35 degrees, because it's 35 degrees as we go clockwise around the circle. I like it this way. I would say you went mostly east, and you went 35 to the north. That's also a valid way of writing it. Or you could say 35 degrees north of east. And really all of these are valid ways of writing out that angle. So hopefully that first example made sense. Again, this is the beauty of doing this asynchronously, is I'm just going to go on to the next example, but if I lost you there, make sure you let me know if I can kind of help explain things. So we're going to try another one. We're going to try to do a vector diagram here, but this is going to be a little more challenging. We've got a few different components to it. It says that we're going to drive north for a while. Oh, I didn't mean to do that. Let's remove that. Let's draw north for a while. So first I'm going to draw north, and I'm going to draw a vector that's 3.5. I'm going to do it roughly to scale. That's north. And then afterwards, we're going to go to the east for a while. And this is even further to the east than it was north. So I'll draw this one a little bit bigger and call this one 4.2 kilometers. And then when I'm done, it says we go south for a while. And to scale, 2.1 kilometers south doesn't take me quite back where I started, but 2.1 kilometers might get me to there. And then it says I continue going east again. So let's use purple. And 1.1 east maybe is about that far. And what makes this one challenging then is I have done everything correctly. I have drawn everything tip to tail. Because, I mean, even as we read this one, it said then, right? That kind of implies that it goes this way, then down, then there. Right? And there are some things that happen simultaneously that we're going to make happen in different dimensions. Like we're going to break things up and pretend that they're done one after another. But this one literally was one after another. It was up, then over, then down, then over. The problem we've got then is that my final resultant is basically like this. This is my final resultant here, the yellow R. And, well, the struggle with this yellow R now is that it doesn't really involve a triangle. So we have to think a little differently here. So what we need to really do is we need to make a triangle. I'm going to do that here. I'm going to make another triangle where I know that my resultant basically should look something like this. And what I want to do is I want to calculate what its x-axis component should be, and I want to calculate what its y-axis component should be. And hopefully you can kind of just visualize how that's going to work. Its x-axis component is going to be 5.3 kilometers. And the reason I knew that is because, well, this 4.2 was going towards my east, right? But so was 1.1. If I were to add those up, 4.2 and 1.1, that'd add to 5.3. And in the y direction, though, I'm actually going to use the number 1.4 kilometers. And hopefully this makes sense as well, because we went 3.5 kilometers up or north, but then we came back down 2.1. Those need to be subtracted from each other. And so what I'm really doing is I'm finding my net x value. I'm finding my net y value. And this is how much total we've traveled in the x and y directions. Well, then to find my hypotenuse is the exact same thing I've just done in the previous example. It's c squared equals a squared plus b squared, which means we need to square root 1.4 squared and 5.3 squared. So 1.4 squared, add 5.3 squared, square root the whole thing, and I'm going to get the answer of 5.48, etc. Now, if this is a number you're planning on using again in the future, I highly recommend you store it as, like, say, a letter, like, say, letter A, since we haven't used any letters yet in this lesson. Since we're not going to be moving on in this example, we can go right to proper sig digs, which is going to be 5.5 kilometers. So that's a net distance of 5.5 kilometers from your start to your finish. But if you're planning on using that number again in the future, you should really store it as A. Now, here's the reason why I always like to use tan inverse to calculate my answer as, like, my angle, because we do need an angle right here. Pardon me, I'm having a bit of a sore throat here. Okay, as I use tan inverse, the reason I like tan inverse is that I'm not actually ever using the hypotenuse value that I just calculated, because I can use the 1.4 number over the 5.3 number as my opposite, my adjacent. Now, in theory, yes, you could use sine. For some of you who have the question, Chris, can I use sine? Can I go 1.4 over 5.5? I would say, well, no, I wouldn't do 1.4 over 5.5, but if you've stored that answer as A, then yes, sure, go ahead. But you have to make sure that you use the exact value. So, anyways, long story short, we should be calculating an angle as well. So I'm going to tan inverse just because I always like tan. It means you're never using a rounded number. I got 14.79 degrees, which rounds this up to, I guess, 2 sig digs, so 15 degrees. So here's our final answer. The final resultant means that you need to go 5.5 kilometers. And we could have just called it 15 degrees. My preferred method is this. I'm always going to write it like this. I'm going to say you're going to go east and then go 15 degrees towards the north. And there we go. That will be your final displacement resultant from start to finish. Remember how we've talked in class about how if you start at home and end up at home, you've really traveled a displacement of 0? You know, I mean, this guy really has traveled whatever 3.5 plus 4.2 plus 2.1 plus 1.1 is. He's traveled a grand total of 10.9 kilometers. But that's his distance. His displacement, though, is only a net of 5.5. Let's try another example here. Now this example is a little bit different. Here we're actually going to work backwards and find what's called the components. And so to find the components, what we're going to do is I'm actually going to give you the net vector. I'm going to tell you that there is a plane that traveled in a northwest direction. This is why I like this direction. It's traveling mostly north, but it's traveling 30 degrees to the west. So I could say that it's traveling mostly north, but it also traveled to the west. And right here is 30 degrees. And what we're actually trying to figure out is that although it's traveled 34 kilometers on the hypotenuse, we're being asked to calculate the north and west components. Right. Now I probably didn't even draw this to scale all that well because that doesn't even look like 30 degrees to me. But I mean, we'll go with the picture with the way it is here, but maybe it should actually be thinner. Probably. Well, let's fix it. Let's do it properly here. Sorry for any of you who've already drawn this. But I mean, it probably works best like this. We traveled mostly north, but we've actually gone off by probably like that. There we go. And we've gone 30 degrees off to the west, because really here's our tip to tail. Here we went north for a while, then we went west for a while. And maybe this is the best way of describing this, that in this particular example, they probably just traveled along the 34 kilometer vector. Right? The 34 kilometer hypotenuse is what was actually traveled. But you could consider it to be the net sum of someone going first north and then going west. So if we want to find those components, how much to the north and how much to the west did this thing travel? Almost as like an XY coordinate pair, we want to calculate that. And here's how this works. We have to use our trigonometry again. We need to know that, say, the sine of 30 degrees is equal to the opposite over the hypotenuse. Well, the opposite value in this particular setup, the opposite value is your west component, but your hypotenuse was 34. So if you kind of understand how to manipulate this, if you times the 34 up to the other side, 34 sine 30 will be equal to your west component. So if I type that in, 34 sine 30, I end up getting 17. Which means you must have gone 17 kilometers in the west direction. That must be how much this side right here is. But we've also traveled some north component as well. And that would come, pardon me, pardon my cough, hopefully I didn't scare you guys there in the video. That would come from cosine. If you did this, cosine of 30 degrees, that would be the adjacent over the hypotenuse. Now in this particular example, your adjacent is going to be the north, and your hypotenuse will still be the 34. So if you times the 34 up and do 34 cos 30, that will tell us what our north component was. So 34 cos 30 should give us 29.4 or so repeating. I'll write it like this. It was 29.44, etc. And that would be how many kilometers was traveled to the north. Now, I'm not planning on using this number again in the future, so I will just round it to 29. But there, we now have the components. Now, again, this is kind of the point I've been trying to make, so hopefully now it kind of comes full circle. Let's say that you had something that was actually traveling along this hypotenuse. We could consider it as though it traveled north and then west. It may never have done that. It may have always traveled along that hypotenuse. But we can consider it as though it took the long route. And really, it's the same thing either way. That's going to be something we're going to need to utilize as we go forward and solve more problems. Let's try another one. By the way, if that stumped you there, make sure you call me over. So here's going to be one of the more typical questions you're going to be given, something like this. A plane is going to fly 30 northwest, or sorry, north 30 west. Then it's going to fly north 40 east. And because of this, it's kind of traveling in different angled directions. Watch how I kind of draw this one out. It's going to travel 34 kilometers north, 30 west. So it means it went mostly north, but 30 degrees to the west, which means this right here could be like, say, the 34 kilometers. And one of the things that I sometimes like to do is draw a bit of like an arrow right where it began like this. And the reason why I'm drawing this is to indicate that the angle right inside there, that's 30 degrees. This is going mostly north, mostly straight up, about 30 degrees to the west. Okay, but here's the next one then. Then, as I get to the next spot, so I'm going to draw a new crosshair as it is right here. There's a new crosshair. It then traveled northeast, so it traveled mostly north, but now 40 degrees to the east. So I'm going to draw it like this now, maybe a little further, because it's 58 now. So this is now 58 kilometers. And what's unique about this one now is that this right here is 40 degrees right there. So I have a couple of angles that kind of apply here. And what we're being asked to do is determine the resultant. Now I'm going to show you guys first the long way of doing this, and then afterwards I'm going to show you the shortcut. But the shortcut really only works if you've done Math 20-1 or 20-2. So I'm not going to start with that, but I will show you how you can use the cosine law to solve that. And most of the times when I solve the question, I will be using the cosine law, but there's a long way of doing it. And I call this the triangles method, because here's what I'm going to do. I'm going to break up the red triangle into an x and into a y component. And then I'm going to break the purple triangle up into an x and into a y component. And then I'm going to break the green triangle up into an x and a y component. And what you'll actually see is that I've made a box here. And inside the box there is a triangle within this box. Oops, I didn't mean to draw that there. Inside this box there is a triangle hopefully hidden inside. And what we're really looking for is this side right here of the triangle. That's what we're being asked to solve for. The resultant right here. That is the worst arrow I've ever drawn in my life. I'm so sorry, guys. There you go. We're looking for this dotted line right here. And we can calculate it by finding all these different components. And so I'm going to start doing that piece by piece here. So I'm going to start with the red triangle. Now on the red triangle, I actually don't know an angle inside the triangle. I know that right here is 30 degrees. But that means that this is 60 degrees right here. It's 60 degrees because they have to add up to 90. And so what I'm going to do is I'm going to solve for what I'm going to call x1 and y1. And the reason why I'm going to go with 1 is that I'm going to have to do this actually 3 times. 1 for red, 1 for purple, 1 for green. So here's how I'm going to find x1. Now after a while you get a little bit quicker at this. I know that, say, cosine of 60 degrees is equal to the adjacent over the hypotenuse. You can write this out every single time if you want, but I'm going to speed it up in a second here. Well, cosine of 60 degrees will actually be the adjacent. Well, the adjacent will be x1, and the hypotenuse will be 34, because this 34 was really that side right there. And so what I can really do is I can speed it up and say that x1 is equal to 34 cos 60. So if I type that in, I'm now going to actually save this one in my calculator because I know I'm going to need this value. Okay, well that one was dumb to save because it was 17. You know what? I could still save it. I'm going to store that as letter A. This is how I kind of show it. I'm going to store that as letter A. Store as A. Store as A. Oh, something's going wrong with my calculator. 17. Store as A. My calculator won't let me store it as A. There we go. I'm going to store it as B apparently. Alright, for whatever reason my calculator won't let me override A. I don't know why. So I'm going to store it as B. You guys store it as whatever letter you want. Let me erase that though. Let's do it nicely. Store that as letter B, I guess. So if you're wondering why this is taking so long, my calculator wasn't letting me store it as A for some reason. Okay, now that's solving for this. So I'm going to solve that as side. I'm going to call that letter B. But I can also solve for the component that's the up component as well. And so that's going to be y1. Now once you figure out kind of how this works, this is going to be 34 times the sine of 60 degrees. Now you can show this work if you like every single time, but I don't need you to. Okay. Hopefully it makes sense, but this is going to be the opposite over the hypotenuse, and so that means you use sine. So once you get the hang of that, you can go a little faster and go, well, 34 times the sine of 60. And I got, oh, this is the same thing we did before. This is a 29.44, and I'm going to store this as letter C, as long as I'm allowed to. Store as letter C. There we go. And so this is now going to be side C. Pardon my cough. I'm so sorry, guys. Well, now I'm going to do the exact same thing in purple. And maybe you can already see my end game here. You can see why we're going to do this. But if you don't, let's just keep going. So I'm going to call this one y2. I'm going to call this one x2. We're going to do the exact same thing. So Let's figure one out. Let's do y. Let's do x2, I guess. X2. Now, in this particular case, I guess you got to figure out whether it's opposite or whether it's adjacent I'm looking for. Since I'm looking for the opposite, I'm going to use sine, because sine involves opposite, cosine involves adjacent. So I'm going to use 58. And then I said it was opposite, right? So that's sine. So it'll be 58 times the sine of 40. Now, if I'm losing you there, can you pause the video and call me over and let me explain to you how I'm kind of shortening this up a little bit? Because I'm not writing out every single little step along the way. That would just be so tedious to do. But if you don't understand why I made this side right here, x2, 58 sine 40, can you let me know? Pause the video and call me over. I mean, the logic is that it's about the opposite. Okay. So I'm storing that as letter D, by the way. And now I'm going to find y2, and y2 is going to be the adjacent, so it's going to be 58 times the cosine of 40. And I'm going to store that as letter E. So 58 cosine 40, and I got 44.43, etc. And again, I'm going to store that as a new letter E. So there's a really big step there. If you are lost, you understand where all those numbers came from. I mean, this is why we're doing the video lesson this way, to kind of speed things up or to slow it down, depending on what you need. So ask questions right now, because this is the important part now. Now we need to try to figure out our hypotenuse, but really we can figure out from adding vectors together. I'm going to use a new color here, and I'm going to say that this is now going to be y3, and this is going to be x3. But I can actually tell you how to calculate y3. y3 is going to be y2 plus y1. Really, because this up vector and this up vector right here is really the same length as this one right here. So I can actually tell you exactly how big y3 is. y3 is going to be whatever E plus C is. But this x3 right here is going to be whatever x2 minus x1 is. Because x2 is all the way across, and x1 is a little bit less, right? x2 was 37, x1 was 17. This will be the difference between them. So this is actually going to be D minus B. So I'm going to redraw in a new triangle again, just to keep it organized a little bit. But you don't probably need to redraw this if you understand it. I'm going to redraw our new triangle where this was the side we were looking for. And I knew that this side here was E plus C, and this side here was D minus B. And I'm going to calculate those values out. So here we go. I'm going to take letter E and add letter C. And of course my calculator won't let me do that. Oh, what is wrong with this calculator? I'm going to have to do this the long way here. You have to bear with me while I change out my calculator. Something's wrong with this calculator. It won't let me archive numbers. So I got to go find them again. What were they? E was 44.43. That was 58 cosine 40. Okay, 58 cosine 40 was 44.43. That's E. Then I'm going to add to that C, which was 34 sine 60. This is one of the reasons why it's kind of nice to write down all your values on the side too, just in case you lose them. Okay, so hopefully you'll have the same thing as me now. I just had to use a different calculator because something's wrong with my first one. I now have 73.875, etc. And this is my new net y value. And I'm going to store that as another letter. So I'm now, what do I finish at? E, I'll store that as F. Store that as letter F. Have to do the same thing with D minus B. So D was my 58 sine 40 number, which should have been 37.28. That's D. I'm going to subtract B, which was 17. And so on this axis over here, on the x-axis, I have a net value of 20.28, etc. And I'll store that as G. So now I will store this as letter G. Okay, last step is now that I know all of these sides, I'm really looking for this hypotenuse. And so there's only two steps remaining. One is to use Pythagoras' theorem. C squared equals A squared plus B squared. And so if I square root G squared plus F squared, that's why I saved these numbers, that should give me my final hypotenuse. So Here we go. G squared plus F squared. Oh, and don't forget to square root and to square root this. I got a final value of 76.6. And with sig digs, I'm just going to go back to the top and check. I get 2 sig digs. So it looks like this final hypotenuse was 77 kilometers, which hopefully that kind of makes sense. So we first went off this way for a while, we went off this way for a while, and we now know that it's 77 kilometers away. And boy, that was a lot of work because you had to solve 3 triangles. You have to solve this green triangle here last. But in order to solve the green triangle here last, first you have to calculate the purple triangle. And you have to calculate the red triangle. And that takes a long time because you got to break it up into x and y components. And you have to add them to each other. And eventually you'll solve for what's inside. Now we're not even done yet. Here's the other crazy thing. We still need a direction. Now the good news is directions aren't actually that hard. You're looking for this angle right here. And so to do that, you want to tan inverse your opposite. Your opposite in this case was letter F. Your adjacent was letter G. And so that's why we want to save all these numbers. If you don't know how to save a number in a calculator, let me know and I will help. So I'm going to tan inverse F over G. And I got an angle of, let's call it 75 degrees. So 75 degrees right there. So here's our final answer. We know that it was 75 kilometers, and there's an angle of 75 degrees here. So the best way of writing this is probably 77 kilometers with an angle of, I like this way. I'm going to say you were going mostly east, and you went 75 to the north. There we go. Okay, now that was a long question. There was a lot to it there. And so this is why we're doing it asynchronously, because if I lost you at any step along the way there, you need to pause. You need to ask me to re-go over this again. However, if you understood this and you're like, yeah, I get this, Chris. I'm comfortable with this. There is a shorter way of doing it. And so I'm going to do another example now, but I'm going to do it using something called the cosine law. And that's what I'm going to show you right here is that if you have triangles like this, it is possible to make a triangle that kind of goes like here, and you make a box out of it like this. And you can make a box out of this one over here as well. And the final one doesn't actually require a box because we're on the axis. But if you know the cosine law, there's a shorter way. It goes like this. C squared equals a squared plus b squared minus 2ab cosine of capital C. And the way it works is that if this side right here is C, the like de facto hypotenuse, even though it's not really a hypotenuse because it's not a right angle, then this side can be A, this side can be B. But this side, this angle right here is the angle we're going to utilize right here. Now, if we're not using a 90-degree triangle, like normally if this is 90 degrees, you don't even need to have this, and it's just Pythagoras' theorem. But if you have a non-90-degree triangle, you can actually use the cosine law to solve. And so I'm going to do one last example. Yeah, one last example here. And on this one here, I'm going to speed things up. I'm going to show you real quick how we would solve this using triangle theory. But I don't need to do like 5. I don't do 5 examples in this class, by the way. If you haven't noticed that, I do a different example every time with a new purpose. So if you want me to re-go through the last example using triangle method, I can. But I'm going to try something different this time around. Here's the example. A player A passes the ball 12 meters to player B at an angle of 30 degrees. So if I were to draw that, here's a little like header to get going. Player A passes to player B, and the angle that we have right here was 30 degrees. I'm going to make a new color. Then it says that player B relays the ball, because there's another like crosshair to get us going, relays the ball at an angle of 155. And 155 means that like all the way around to here is 155. So I'm going to draw it kind of like that. So from here to here is 155 degrees. Now I didn't actually write in the values though. I believe this was 9 meters, 9.0 meters. And this one right here was 12.0 meters. And so the question is, well, how far away has the ball actually moved? So if I were to draw another resultant, the resultant will be this side right here in green. And you can see that there's a triangle starting to form. And if I wanted to, I'm not going to do it this way, but if you'd like to, and everyone should be able to do it this way, you could make a triangle right here in red and find x1 and find y1. Pardon me. You could then make a triangle in purple. And this is like the triangle box method. You can make a triangle in purple. where this side right here would be y2, and this side here would be x2. And then finally, you can make a triangle in green. And so in green, you would have a certain amount going up and a certain amount going over. And we'd call this x3 and y3. And in this particular example, which is not quite the same as the last, but it's pretty similar to the last one, we would know that in order to solve for the final triangle, y3 would be equal to y2 and y1 added together. But x3 would be equal to x1 minus x2. And we could then solve for these two sides right here and use Pythagoras' theorem for the remainder. That works. That's a lot of work. So what I want to do now is I want to just kind of erase most of the unnecessary work on here. And I'll show you how to use the cosine law because it is much quicker. And look, you don't have to do it this way. But you're all going to be taking a math course, a math 20 course at some point. So you either have learned this already or you will be. So I'm just going to erase kind of all the unnecessary stuff and go back to there. I think that'll do. I'm just going to rewrite in that this side right here was 9.0, I believe. Okay, so here's how this works. I'm going to relabel the sides of this triangle now using the cosine law. And so the side that I don't know, I'm going to call side C. And these other two sides, I'm going to call them A and B. I don't really care which one is which. And so if I wanted to use Pythagoras' theorem, it would look like this. C squared equals A squared plus B squared. However, because this is not a right angle triangle, you need the little addendum minus 2AB cosine C. I can already plug in almost all the values I need. I need a 12 squared and a 9 squared, minus 2, 12, 9. But what I'm missing is cosine C because I need to know the angle. And the angle we're looking for is always the angle across from the side we need. So we need this little angle right here that I'm kind of drawing in black. And I'm going to erase it in a second, but I need to illustrate that this angle right here is the one we need. And so in order to calculate that, we need to know a couple of principles of math. The first one is that if this angle right here that I'm circling here is 30 degrees, here's really the long version of it. If I made an angle triangle out of this, even though I didn't use the triangle, if I did, it means this angle here would be 60. Which means that half of the angle inside right here would be 30. And so I actually know part of the angle inside. Then the other part of the angle comes from the fact that if almost all the way around is 155, it should add up to 180. And so 180 minus 155 gives us 25 degrees. So there's actually like 2 portions of the angle inside here. Now, it's never the same thing twice. If you haven't figured this out about by physics by now, it's almost always a slightly different mechanism every single time. I cannot give you a rule or an algorithm that it always works this way. But if you understand those principles, you can see how to piece that puzzle piece together. I now know that the angle I was looking for was 55 degrees. There we go. That's all I need. Now I just treat Pythagoras' theorem the exact same way that I always have before. I even square root the exact same way. It just means there's this extra little bit on the end here. So it looks like this 12 squared plus 9 squared minus 2 times 12 times 9 times the cosine of 55. Don't forget to square root it all, but I got a final answer of 10.05, etc. And just because I'm in a good habit of doing this, I'm going to store this as letter A. Let's see if that works now. Store as letter A. Yeah, it works. My last calculator wasn't letting me store for some reason. Well, there we go. Now I know the resultant. It's 10 meters on this axis right here. That's how far it's traveled. However, I also need to know an angle. And this is where another rule comes in. And if you've seen this one before, it's called the sine law. So the sine law says if you know sine of, say, A over little a, or if you know sine of B over little b, or if you know sine of C over little c, if you know any of that information, you can solve for the remaining bit. Now, this is, again, in a Math 20-1 or 2 course, so you may not be familiar with this. So this is a good time to let me know, hey, Chris, can I help out a little bit? Can you help me with this? Because I'm not familiar with this. But here's how this would look. I actually know a lot of information on this one right here. I know what side A. Now, I don't know why we go with different letters. I went with big letters right here. I really should have done little letters. This should have been like little a. This probably should be little b. That's usually our convention. This should be little c. And the way it works then is that the side across is the big letter for angle. So this right here would be capital A for angle. This would be capital B. And the one we just solved for right here, that would have been capital C, 55 degrees. So what I think I really need is I need side A right here. And the reason why I need side A right here is that's how much more I'm going to add to 30 degrees. You can see how A is just this little sliver inside here, but there's like 30 degrees more that gets added on top of it. So I'm going to try to solve for angle A right here, which means I need to know sides A, like I need to know some information about either sides B or C. And I do. I know all about side C. I don't actually know enough about angle B, but I do know side C. So I'm going to remove the sign B from this equation and write it out like this. Sine of A is what I'm looking for. But I know actual side A. Side A was 9.0. And sine C, I know as well. Well, sine C, C was the angle, is 55 degrees. Now, side C was that 10 meters. Now, it's actually 10.05, etc. Don't forget, I stored that as letter A. So now I need to solve for sine A right here. And so in order to solve for this angle A right here, you have to multiply 9 up to the other side. It'll give you this. It'll give you sine of A will give you 9.0 sine 55. And that'll be all over the 10.05 number that was right there. So I'm going to do that right now. I'm going to find what that is. I'm going to do 9 times the sine of 55, and I'm going to divide by the 10.05 number, which I've stored. And I'm going to get this answer right here. It should always be less than 1, otherwise something went really wrong. I got 0.733, etc. And then the last step is that in order to get rid of a sine sign, you have to sine inverse both sides. And if you do that, that gets you down to angle A by itself, which basically means you need to sine inverse the number you just found. So if you go second sine, inverse sine this thing, I got 47 degrees. Ooh, that didn't work out nicely. Let me write that better. I got 47 degrees. Okay, so there's our final answer. Well, no, it's not. Okay, we know that we went 10 meters. 10 meters. But it's not 47 because this angle right here that is colored in black, that is 47 degrees. It has to be added to 30 more. So the grand total is 77 degrees. So it's 10 meters. And I like writing it like this. You went mostly east, and then you went 77 degrees towards the north. And that's my preferred method of writing it. But there's other ways you could do it too. Okay, that's going to be the end of this lesson, because I want to kind of pause it there. Hopefully that made sense. I mean, this is where physics, it takes a big turn all of a sudden. I mean, if you were doing fairly well so far, the reason why is that we've really only worked with one dimension. But now we're going to talk about x and y dimensions and how to put those together. And this really it keeps building and building and building. Physics is really one of the most important courses for problem solving. If you have good problem solving skills, you'll do well at physics. But yeah, it's not quite the same every single time. So now that I'm done my video, you can stop if you'd like, or you can listen to me ramble for the next minute here. I want to really recommend some advice to you guys. If you were struggling at any point along the way there with stuff that was kind of background knowledge, you need to make sure you let me know. And if the physics stuff, the new stuff caught you, you also need to let me know, right? That's why we're doing this asynchronously. So last thought here is that you've been given other things to work on. There is an assignment to work on. If you haven't been talked to by me about your Mythbusters project, there's that to work on. There's labs to work on. But you need some practice on these skills too. So make sure you keep up to date on that. So, okay, I'm going to stop the video, and you let me know in class if I can help on anything. Thanks, everybody.